Hello, in this lecture we'll answer on two questions. In the first question we find out the area of this circle, and in the second question we find out the area of this trapezoid ABCD. Let's start with the first question. In the drawing we have a circle, and this is the convection point P. From this convection point P we have two tangents to this circle, tangent PA and tangent PB. We also know that line segment CP equals to 4 units in its length, line segment BC equals to 1 unit. In addition, we have the right triangle ACP that cuts the circle with 2 points, point A and this point. Again, our mission is to find out the area of this circle. So here we can implement rule 2 in the drawing. I'll click on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle, and we have the common standpoint point P. From this common standpoint point P we have two tangents to the circle, tangent PA and tangent PB. According to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. Why? Because in our drawing, the common standpoint point P, from this common standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So I write it down. According to rule 2, tangent PA equals to tangent PB. It is given us a question that PB in total equals to 4 plus 1, that is 5. So I write it down. PB equals to 5. And from this equation PA equals to PB equals to 5, we will derive that PA equals to 5. PA equals to 5. So here, this is line 78 that equals to 5 units in its length according to rule 2. In the next step, I'll copy the right triangle APC in a new page, and we'll implement the Pythagoras theorem on this right triangle APC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the provision for Pythagoras theorem. So actually this is the right triangle ACP that I got from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, equals to AC square plus CP square. So I write it down. So the hypotenuse is AP square, and it is equals to AC square plus CP square. AP is 5, therefore AP square is 5 square, that is 25. And it is equals to AC square. AC is the AC side, so we leave it as it is. AC square plus CP square. CP is 4, therefore CP square is 4 squared, that is 16. So in total I should find out that 25 equals to AC square plus 16. Here we subtract 16 from this equation, and we get that AC square equals to 25 from 16. 25 from 16 is 9. Here we take a root out of this equation, and finally we get that the missing sign AC equals to the square root of 9, that is 3. So here AC equals to 3 units, and it's 9. This is the missing side AC, that is equal to 4 units. So I can go AC equals to 3 units, and it's 9. In the next step, we will define the center of this circle. This point is point O. And we'll join points O and B together by a straight line. Point O is the center of the circle, point B is the point on the circle itself, therefore OB is the radius of this circle. We will define the radius of this circle as x, therefore OB equals to x, according to our definition. Here we can implement rule 1. I think we quickly on rule 1, according to rule 1. The tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we also have tangent AB that is tangent to this circle at point M. In addition, we have here the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius OB that is equals to x. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees, according to rule 1. It is given as the question that PB is a tangent to the circle at point B. So PB as a tangent it is absolutely a straight line. So if we focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal 280 degrees. In this case, it means that the sum of the angles on the upper side of the straight line PB at point C must be equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction, that is to say, from this point O, that is the center of the circle, we will draw perpendicular on AC. So luckily, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point E. By doing this construction, we can do quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at its left angle, if not a square. So we will relate to quadrilateral OECB as a left angle because it has 4 right angles. So write it down. Quadrilateral OECB is a left angle according to rule 5. But we also know that the opposite sides of a left angle are equal to each other. So a left angle OECB, side OE must be equal to the opposite side CB. But CB is 1, therefore OE must be equal to 1. Likewise, according to the sum rule, in the same left angle OECB, side OB must be equal to the opposite side CE, but OB is x, therefore CE must be also equal to x. What is the therefore the missing line segment AE? From the drawing it is very easy to see that AE equals to AC minus EC. Again, AE equals to AC minus EC. So I write it down. AE equals to AC minus AC. So AE equals to AC is 3, minus AC is x. So in total, AE equals to 3 minus x. AE equals to 3 minus x. The next step, we join points O and A together by straight line. What is the definition of line segment OA? Line segment OA starts from point O, that is the center of the circle, and ends at point A, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OA is the radius of this circle, that is equals to x according to our definition. So in the next step, I will copy the right green triangle OAE in the new page. And we will implement the Pythagoras theorem on this right green triangle OAE. So actually, this is the green right triangle OAE that I got from the original drawing. According to the Pythagoras theorem, in this right triangle OAE, OA squared, that is the square of the hypotenuse, equals to AE squared plus EO squared. So write it down. OA squared, that is the square of the hypotenuse, equals to AE squared plus OE squared. The hypotenuse OA is x, therefore OA squared is x squared, and it is equal to AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared. Plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total we found out that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared is equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x, plus 1. So x squared equals to 9 plus 1 is 10, minus 6x. X squared equals to 10 minus 6x. Here we add 6x to this equation. And actually here, first of all, we have x squared on both sides of the equation, so x squared will get cancelled. After we cancelled x squared, in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, plus 6x. So here we add 6x to this equation, and we get that 6x equals to 10. So here we divide this equation by 2, and we get that 6x over 2 is 3x, equals to 10 over 2 is 5, so 3x equals to 5. Here we divide this equation by 3, and finally get that x equals to 5 over 3 units in itself. So if we found out that the radius x of this circle is equals to 5 over 3 units. Our mission is to find out the area of this circle. Actually, the area of any circle is equals to pi times the radius of the circle squared. Okay, again, the area of any circle equals to pi times the radius of the circle squared. So the area of our circle will be equal to pi times the radius of the circle squared. The radius of our circle is x, therefore the radius squared is x squared. So the area of our circle is equals to pi x squared. So it is pi, and x is 5 over 3, therefore x squared is 5 over 3 squared. So in total we found out that the area of our circle, that is the area that we are looking for, is equals to pi times 5 over 3 squared. So it is equals to pi and 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total we found out that the area of this circle equals to either 25 pi or 9 square units. So in terms of numbers, the area of this circle equals to 8.727 square units. The area of the circle equals to 8.727 square units. And then again, we should found out that the area of the circle equals to either 25 pi over 9 square units, or in terms of numbers, the area of the circle equals to 8.727 square units. So finish with the first question. In the next step, I will present to you the second question, and we will solve it. In the second question, our mission is to find out the area of this trapezoid ABCD. Because again, our mission is to find out the area of this trapezoid ABCD. We know that side AB equals to 60 units in length, side AD equals to 17 units, side AC equals to 25 units, and finally side DC equals to 44 units. Actually, the area of a trapezoid equals to the sum of its two parallel bases times the height over 2. So therefore the area of this trapezoid must be equal to the sum of its two parallel bases. We know that AB is parallel to DC, and therefore it is AB plus DC times the height. The height is h, elevation from the height, divided by 2. The height h must create 90 degrees with the two bases AB and DC. So already know the area of this trapezoid ABCD is equals to the sum of its two parallel bases, that is actually AB plus DC times the height h divided by 2. Repeat again that the height h must create 90 degrees with the two parallel bases, that is to say with AB and DC. In order to find out the area of this trapezoid ABCD, we'll do a construction, that is to say, from this point A, we'll draw a perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in DC. This point is point E. We will define the length of side DE, or line segment DE, as x, and we will define the length of line segment AE as h. Actually h creates 90 degrees with the base DC, and therefore h is also the height of trapezoid ABCD. Again, because it creates 90 degrees with the base DC. So in the next step, I'll copy the right triangle AED in the new page, and we will implement the Pythagoras theorem on this right triangle ADE. Here by PT is the promotion for Pythagoras theorem. So actually, this is the right angle AED that I got from the original drawing. According to the Pythagoras theorem, in this right angle AED, AD squared, that is the square of the hypotenuse, equals to AE squared plus ED squared. So I write it down. AD squared, that is the square of the hypotenuse, equals to AE squared plus DE squared. The hypotenuse AD is 17, therefore AD squared is 17 squared, that is 289. And it is equal to AE squared. AE is h, therefore AE squared is h squared plus DE squared. DE is x, therefore DE squared is x squared. So according to equation 1, we should find out that h squared plus x squared equals to 289. In the next step, we will do another construction. That is to say, from this point B, we will draw a perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We know that ABCD is a trapezoid, and therefore side AB is parallel to side DC. And those two angles, they are located between the parallel lines AB and DC. And therefore, they are defined as interior angles. And in addition, those two angles are located between the right side of this line. So we define the touching point of the perpendicular from point B and DC. This point is point F. So those two angles, they are both located in the right side of the straight line BF. So in total, those two angles are defined as the interior angles, and because of the fact that those two angles, they are both located in the right side of the straight line BF, they are also defined as one-sided. So in total, those two angles, they are defined as an interior and one-sided angles. And according to rule 16, the sum of two interior angles that are also one-sided angles, the sum of the interior angles and one-sided angles is equal to 180 degrees. So I repeat quickly on rule 16. According to rule 16, the sum of one-sided interior angles is equal to 180 degrees. So in the drawing, we have two parallel lines. Line A is parallel to line B. This is line I that cuts the two parallel lines A and B. Those two angles, that is to say angle 4 and angle 5, are defined as one-sided interior angles. And according to this rule, rule 16, the sum of those two angles is equal to 180 80 degrees. So angle 4 plus angle 5 equals to 180 degrees according to this rule of 16. Likewise, we have those two angles, 3 and 6, that are also defined as one-sided interior angles, and therefore the sum of them is 180 degrees. So angle 3 plus angle 6 is also equal to 180 degrees. So I can actually implement rule 16 in our drawing. Why? Because in our drawing, those two angles are both defined as one-sided interior angles, and therefore according to rule 16, the sum of those two angles is equal to 180 degrees. So this angle equals to 90 degrees, plus the missing angle, in total they must be equal to 180 degrees according to rule 16. So I write it now. This is angle, the missing angle, angle ABF. Plus this angle, that is the right angle, is equals to 90 degrees in its size. In total, the sum of those two angles is actually 180 degrees according to rule 16. So I repeat again. So the missing angle ABF plus the right angle, because of the fact that those two angles are defined as one-sided interior angles, the sum of them is equal to 180 degrees according to rule 16. So here we subtract 90 degrees from this equation. And we get that the missing angle ABF is equal to 180 degrees minus 90 degrees is 90 degrees. So if we found out that the size of the missing angle ABF is equal to 90 degrees. This is the missing angle ABF. This is equal to 90 degrees according to rule 16. Likewise, those two angles are located between the parallel lines AB and DC, and therefore they are defined as interior angles. And those, in addition, those two angles, they are both located on the left side of the straight line AE, and therefore they are also defined as one-sided angles. And in total, those two angles are defined as one-sided interior angles, and according to rule 16, the sum of those two angles is equal to 180 degrees. So I write it now. The missing angle here is angle BAE plus this angle that is the right angle. In total, the sum of those two angles is equal to 180 degrees according to rule 16. Okay, again, if I found out that the missing angle BAE plus the right angle in total must be equal to 180 degrees according to rule 16. Here we subtract 90 degrees from this equation. And we'll get that the missing angle BAE is equal to 180 degrees minus 90 degrees is 90 degrees. So if we found out that the size of the missing angle BAE is 90 degrees. This is the missing angle BAE. This is equal to 90 degrees according to rule 16. So in total, we found out that inside quadrilateral ABFE, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle not a square. So we relate to quadrilateral ABFE is rectangle because it has 4 right angles. So I write it down. This is quadrilateral ABEF. This is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side FB. But AE is H, therefore FB must be also equal to H. What is the length of the missing line segment FC? From the drawing it is very easy to see that FC in total is equal to DC minus DE minus EF. Again, FC equals to DC minus DE minus EF. So write it down. FC equals to DC minus DE minus EF. So FC equals to DC. DC is 44 units according to what is given as the question. Minus DE. DE equals to X according to our definition. Minus EF. EF equals to 16 units according to what we already found out. So in total we shall find out that FC equals to 44 minus 16 is 28 minus X. So FC equals to 28 minus X units in its length. In the next step, I'll copy the right triangle BFC in the new page and we'll implement the Pythagoras theorem on this right triangle BFC. Here by PT is the solution for Pythagoras theorem. So actually, this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, equals to BF squared plus FC squared. So I write it down. BC squared, that is the square of the hypotenuse, equals to BF squared plus FC squared. the hypotenuse BC equals to 25 units in it there, therefore BC squared is 25 squared, that is 625, and it is equals to BF squared. BF is 8, therefore BF squared is 8 squared, plus FC squared. FC is 28 minus x, therefore FC squared is 28 minus x squared. So in total we have found out that according to equation 2, 625 equals to 8 squared plus 28 minus x squared. Here we'll open the brackets on this side of this equation, equation 2, and we get that 625 equals to 8 squared plus 28 minus x squared. 28 minus x squared equals to 28 squared, that is 784, plus x squared minus 2 times 28 times x. This is minus 56x. Here we subtract 625 from this equation, and we get that in this side of the equation, after we subtract 625, we left with nothing, that is to say 0. And on the other side of the equation, we have 8 squared plus x squared, 8 squared plus x squared, minus 56x, 784 minus 625 equals to 159. So here we add 56x to this equation, equation 2, and we get that 56x equals to 8 squared plus x squared plus 159. We have already found out that 8 squared plus x squared equals to 289. Therefore, we can substitute 8 squared plus x squared by 289. We do it now, and we get this according to this equation, equation 2. $56x equals to 8 squared plus x squared is 289 plus 159. So in total we have found out that according to equation 2, 56x equals to 289 plus 159 equals to 448. So here we divide this equation, equation 2 by 56, and finally we get that x equals to 448 over 56 is 8. So x equals to 8 units in its length. Our mission is to find out the area of this trapezoid ABCD. And we already found out that the area of trapezoid ABCD is equals to the sum of its two parallel bases, that is AB plus DC, times the height, that is h, over 2. Okay, again, if we found out that the area of trapezoid ABCD equals to the sum of its two parallel bases, that is AB plus DC, times the height h over 2. So the area of trapezoid ABCD is equal to AB is 16 plus DC is 44 times the height h, the height is h, divided by 2. So the area of trapezoid ABCD in total equals to 16 plus 44 times the height h over 2. According to equation 1, we have already found out that x squared plus x squared equals to 289. We already found out that x equals to 8. If x equals to 8, it means that x squared equals to 8 squared, that is 64. So we substitute x squared in this equation 1 by 64, and we get that x squared plus x squared, that is 64, equals to 289. Here we subtract 64 from this equation, equation 1, we finally get that according to this equation, equation 1, x squared equals to 289 minus 64 is 225. So x squared equals to 225. Here we take a root out of this equation, equation 1, and we get that h equals to the square root of 225, that is 15. H equals to 15 units in its length. And therefore, the area of trapezoid ABCD equals to 16 plus 44 times h. H is 15 over 2. So in total, the area of trapezoid ABCD equals to 16 plus 44, that is 60, times 15 over 2. 60 over 2 is 30. So in total, this expression equals to 30 times 15. 30 times 15 is 450. So in conclusion, we should find out that the area of trapezoid ABCD is equal to 450 square units. But again, we should find out that the area of this trapezoid ABCD equals to 450 square units. We finish with the second question. In the next step, I summarize the lecture. We'll start with the first question. In the first question, our mission is to find out the area of this circle. So in the drawing we have a circle, and we also, this is the common axon point P. From this common axon point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we know that we have here the right triangle ACP. The right triangle ACP cuts the circle 2 points, point A and this point. We know that side CP of the right triangle ACP equals to 4 units in its length. This is line 7 CB, that is equals to 1 unit. And our mission is to find out the area of this circle. So here we can implement rule 2. Why? Because if we focus on this common axon point P, from this common axon point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So again, according to rule 2, PA equals to PB. but it is given as a question that PB in total equals to 4 plus 1, that is 5. Again, PB equals to 5. So, can I tell that PB equals to 5? And for this equation, PA equals to PB equals to 5. Then derive that PA equals to 5. So, this is PA, it equals to 5 units in its length. In the next step, I copied the right triangle ACP in your page and represented the Pythagoras theorem in this right triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, this is the right triangle ACP that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we leave it as it is. So we have AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total we have found out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation. And finally found out that AC squared equals to 25 minus 16 is 9. So AC squared equals to 9. Here we took out of this equation. And finally found out that the missing side AC equals to the square root of 9, that is 3. So here AC equals to 3 units in its length. Here AC equals to 3. In the next step, we define the center of this circle. This point is point O. And we also define the radius of this circle as x. Then we join points O and B together by a straight line. Point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of the circle, that is equal to x according to our definition. Here we can implement rule 1, because we have the radius OB that is equal to x, the radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever your radius is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given us a question that PB is tangent to the circle at point B. So PB is a tangent, is absolutely a straight line. So if you focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. In this case, it means that the sum of the angles on the upper side of the straight line PB at point C must be equal to 180 degrees. So which angles we have in the upper side of PB at point C? We have this angle that is the right angle, plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did the construction, that is to say, from this point O, that is the center of the circle, we draw perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. By doing this construction, we created quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 180 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB, we have 4 right angles. According to rule 5, any quadrilateral that has 4 right angles must be this right angle not a square. So we relate to quadrilateral OECB is right angle because it has 4 right angles. Okay, but we also know that the opposite sides of right angle are equal to each other. So in right angle OECB, side OE equals to the opposite side BC. But BC is 1, therefore OE must be also equal to 1. Likewise, according to the same rule, in the same right angle OECB, side OB must be equal to the opposite side EC, but OB is x, therefore EC must be also equal to x. What is the length of line segment AE? For the drawing, it is very easy to see that AE equals to AC minus 3C. Again, AE equals to AC minus 3C. So A equals to AC, that is 3. AC is 3 minus AC, that is X. So in total, AE equals to 3 minus X units in its length. The next step is join points O and A together by a straight line. OA is the radius of the circle that is equal to X. In the next step, I copied the right hand triangle AOE in a new page and implemented the Pythagoras form of this right triangle OAE. This is the right triangle AOE that I copied from the original domain. According to the Pythagoras theorem, this right triangle AOE, AO squared, that is the square of the hypotenuse, equals to AE squared plus OE squared. Again, AO squared equals to AE squared plus OE squared. The hypotenuse AO is X, therefore AO squared is X squared, and it is equals to AE squared. AE is 3 minus X, therefore AE squared is 3 minus X squared, plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total, if we found out that X squared equals to 3 minus X squared plus 1. So X squared equals to 3 minus X squared. 3 minus X squared equals to 3 squared, that is 9, plus X squared, plus 2 times 3 times X, that is minus 6X plus 1. Here we have X squared on both sides of the equation, so X squared will get cancelled. After cancelled X squared, in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 6X. So in total, if we found out that 0 equals to 10 minus 6X, here we added 6X to this equation, and finally found out that 6X equals to 10. Here we divided the equation by 2, and found out that 6X over 2 is 3X, and 10 over 2 is 5. So in total, we found out that 3X equals to 5. Here we divided this equation by 3, and finally found out that X equals to 5 over 3 units in its length. So we found out that the radius X of this circle is equals to 5 over 3 units. Our mission is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of this circle must be equal to pi times the radius of the circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total, the area of this circle is equal to pi x squared. The area of our circle is equal to pi x squared. So it is pi times x squared. X is 5 over 3, therefore x squared is 5 over 3 squared. So in total, the area of the circle is equal to pi times 5 over 3 squared. So it is pi, and 5 over 3 squared is 5 squared, that is 25 over 9. So in total, if we found out that the area of the circle is equal to 25 pi over 9 square units, or in terms of numbers, the area of the circle is equal to 8.727 units. I repeat again, the area of the circle equals to either 25 pi over 9 square units, so in terms of numbers, the area of the circle is equal to 8.727 square units. We finish with the first question. In the next step, I can add to you the second question and we solve the second question. Our mission in the second question is to find out the area of this trapezoid ABCD. It's given us the question that side AB equals to 16 units in step, AD equals to 17, BC equals to 25, and DC equals to 44. The area of a trapezoid in general is equal to the sum of its two parallel bases times the height over 2. In our specific trapezoid ABCD, the two parallel bases are AB and DC. And therefore, the sum of the two parallel bases is AB plus DC times the height, that is h over 2. So the area of our trapezoid ABCD, that is the area that we are looking for in this question, is equal to the sum of the two parallel bases, that is AB plus DC, times the height h over 2. The height h must create 90 degrees with the two parallel bases AB and DC. So in the first step, we did the construction. That is to say, from this point A, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in DC. This point is point E. In the next step, we define the length of line segment DE is X, and the length of line segment AE is H. H is the height of trapezoid ABCD. Why? Because H creates 90 degrees is the best DC. So actually, this is the right triangle AED that I call it from the original drawing, and this right triangle AED, according to the Pythagoras theorem, AD square equals to AE square plus DE square. Okay, again, AD square equals to AE square plus DE square. The opposite AD is 17, therefore AD square is 17 square, that is 289, and it is equals to AE square. AE is H, therefore A square is H square, plus DE square. DE is X, therefore DE square is X square. So in total, according to equation 1, we shall find out that H square plus X square equals to 289. In the next step, we did another construction. That is to say, from this point B, we go perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point F. So here, we know that AB is parallel to DC. So those two angles, they are both located between the parallel lines AB and DC, and therefore they are defined as interior angles. In addition, those two angles, they are both located in the right side of the straight line BF, and therefore they are also defined as one-sided. So in total, those two angles are defined one-sided interior angles. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. Okay, again, on rule 16. According to rule 16, the sum of one-sided interior angles is equal to 180 degrees. So those two angles 4 and 5 are defined as one-sided interior angles, and therefore the sum of those two angles is equal to 180 degrees. Again, angle 4 plus angle 5 equals to 180 degrees according to rule 16. Likewise, those two angles are also defined as one-sided interior angles, and therefore the sum of those two angles is equal to 180 degrees. Again, angle 3 plus angle 6, the sum of those two angles is equal to 180 degrees. So I can implement rule 16 in our drawing. In our drawing, we have those two angles that are defined as one-sided interior angles, and therefore the sum of those two angles is equal to 180 degrees according to rule 16. So repeat again. According to rule 16, the sum of the two one-sided interior angles is equal to 180 degrees. So angle ABF plus the other angle that is 90 degrees, in total it must be equal to 180 degrees according to rule 16. Here we subtracted 90 degrees from this equation, and finally found out that the missing angle ABF equals to 180 degrees minus 90 degrees is 90 degrees. So this is the missing angle ABF that is equal to 90 degrees in its size. Likewise, those two angles are also located between the parallel lines AB and DC, and therefore they are defined as interior angles, and they are both located on the left side of the straight line AE, and therefore they are also defined as one-sided angles. So in total, those two angles they are defined as one-sided interior angles, and according to rule 16, the sum of those two angles is equal to 180 degrees. So this angle equals to 90 degrees, and the missing angle, this is the missing angle, that is angle BAE. So in total, the sum of those two angles is equal to 180 degrees. So the missing angle BAE plus the other angle is equal to 90 degrees is equal to 180 degrees according to rule 16. Here we subtract 90 degrees from this equation and finally found out that the missing angle BAE equals to 180 degrees minus 90 degrees is 90 degrees. So this is the missing angle BAE is equals to 90 degrees in its size. So inside quadrangle ABFE we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be its rectangle not a square. So remember, quadrangle ABFE is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the sum rule, in the sum rectangle ABFE, side BF must be equal to the opposite side AE. But AE is edge, therefore BF must be also equal to edge. What is the length of the missing side CF? CF equals to DC minus DE minus FE. Again, CF in total equals to DC minus DE minus FE. Okay, again, CF or FC equals to DC minus DE minus CF. So FC equals to DC, that is 44, minus DE, that is X, minus EF, that is 16. So in total, FC equals to 44 minus 16, that is 28, minus X. So FC equals to 28 minus X in its length. In the next step, we'll go with the right triangle BFC in a new page and we implemented the Pythagoras theorem in this right triangle BFC. This is the right triangle BFC that are coming from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC square, that is the square of the hypotenuse, equals to BF square plus FC square. BC is 25, therefore BC square is 25 squared, that is 625, and it is equals to BF square. BF is h, therefore BF square is h square, plus FC square. FC is 28 minus x, therefore FC square is 28 minus x square. So in total, according to equation 2, we should find out that 625 equals to h square plus 28 minus x square. So according to equation 2, 625 equals to h square plus 28 minus x square. 28 minus x square equals to 28 square, that is 784, plus x square, minus 2 times 28 times x, that is minus 56x. Here we subtract 625 from this equation. So in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have h square plus x square and minus 56x. And 784 minus 625 equals to 159. So in total we found out that 0 equals to h square plus x square minus 56x plus 159. And according to equation 1, we already found out that h square plus x square equals to 289. But before that, we actually added 56x to this equation. And finally found out that 56x equals to h square plus x square plus 159. We already found out that according to equation 1, h square plus x square equals to 289. Therefore, we substitute x square plus x square in this equation 2 by 289. And found out that 56x equals to h square plus x square is 289 plus 159. So 56x equals to 289 plus 159 is 448. So in total we found out that 56x equals to 448. Here we divided this equation 2 by 56. And finally found out that x equals to 448 minus 448 over 56 equals to x, equals to 8. So in total we found out that x equals to 8 units in its length. Our mission is to find out the area of this trapezoid ABCD. The area of trapezoid ABCD equals to the sum of its two parallel facets, that is AB plus DC, times the height h over 2. Repeat again, the area of trapezoid ABCD, that is the area that we are looking for in this equation, is the sum of its two parallel bases, that is AB plus DC, times the height h over 2. AB is 16, DC is 44, h times h over 2. So the area of trapezoid ABCD equals to 16 plus 44 times h over 2. The next step, we found out the value of h. According to equation 1, h squared plus x squared equals to 289. But we already found out that x equals to 8. If x equals to 8, it means that x squared equals to h squared, that is 64. So we can substitute x squared in this equation by 64. We did it, and we actually found out that h squared plus x squared, so x squared is 64, equals to 289. You subtract the 64 from this equation, and finally found out that h squared equals to 289 minus 64 is 225. So h squared equals to 225. Here we took out this equation, and finally found out that h equals to the square root of 225, that is 15. So h equals to 15. So we can substitute h in this equation by 15. We did it, and we found out that the area of trapezoid ABCD in total equals to 16 plus 44 times h. h is 15 divided by 2. So the area of trapezoid ABCD in total equals to 16 plus 44 is 60 times 15 over 2. 60 over 2 is 30. So in total this expression is equal to 30 times 15. That is 450. In conclusion, we found out the area of this trapezoid ABCD is equal to 450 square units. Okay, thank you very much.